Hello boys and girls. The hook for this video is that I will hand you over a nice script to make these animations. The video will consist at first in explaining what we see here. It has to do with the beta distribution, the Euler beta distribution. But really in the end I want to talk about how to compute the expected maximum of a distribution, or even some more generalized forms of that. So the way that I will introduce this is by a probabilistic scenario. So I'm talking about, oh god, my laptop is so old and slow now that everything takes forever and is noisy. It's so annoying, but okay. Let's say you have a 20-sided die and you roll it, and you're supposed to bet what will the outcome of this roll be. Well, if you just roll one die, then all 20 sides are equally as likely. You cannot really, there's no information, you cannot really get much out of it. But now here is a modified game. You, instead of one, roll 2 dice, and whatever the numbers show up, let's say 17 and 4, you just consider the maximum. You just consider the bigger one. So in this case, if it's 17 and 4, you choose 17. If it's 5 and 6, you choose 6. If it's 13 and 1, you choose 13. And now the situation is different. Now there's actually something you can play with, and I will ask you outright for 3 small questions, and you can think about it. You can pause the video. My questions are: if you play this game, right, you roll 2 dice, you pick the maximum of those. What is going to be the most likely result? Which number on the dice? What is going to be the median value that you actually see? And what is the mean going to be, right? So you can think about it if you want for a little bit. And I will tell you that one intuition to think about it is, you roll 1 dice, everything is equally as likely. And then consider, for example, you rolled a 17, right? If the second roll, the value from the second dice is anything below 17, then 17 will indeed be the largest number, the maximum. If the other dice is an 18 or 19 or 20, then you basically flip over, right? And as it turns out, the maximum likelihood, or the most probable thing you will pick at the end, you will get from this process, is actually 20, because basically the 20 has the least competitors, right? If you roll a 20, then this will not be changed anymore, whereas if you roll a 17, then it might be that it's outcompeted by the second dice, right? And so in this case, 20 is actually the mode, it's the most likely thing. However, if you have a situation like that where the distribution goes, the likelihood goes up, the further you go to the right, basically, of this distribution, and in this case 20 is the most likely, then the median will be below that, and the mean will be even be below that. And so, I'm not really talking about dice in this video, but in this case it turns out that both of these values lie at 14 and 15, around these numbers. Okay, and so we have this situation again. We roll 1 dice, and it's basically a uniform distribution, right? There's 1/20 chance that you get either of these rolls, whereas we have seen that if you do this process of rolling 2 and picking the maximum, then the higher numbers, number symbols on the dice have a higher likelihood, or I have argued for it. And so the question is, what is actually the distribution actually going to look like? And for these scenarios, or even more generally, really, I have made this small Python implementation, and here you see an animation of how this will play out. So what we have here is that I draw 1,000 samples, and I draw them 2 at a time, right? So these lines that you see here are 2 random numbers that I, in this case, I actually draw them uniformly between 0 and 1. And whatever these 2 random numbers are, they are completely random, I nonetheless color them. The left one is going to be colored in orange, and the right one is going to be colored in red. And so in this way, I get an order statistic where even if both of them work together to give you a uniform distribution, right? I'm basically just sampling twice as fast from the uniform distribution, and in the end, getting more numbers. This will be more or less a flat distribution here. If I choose, and here it starts again, if I choose to color them, and am interested in the maximum, and I've argued, that the right-hand side values are going to be more likely, then I get this split. The maximum distribution is the red one. I plot it in front of the minimum distribution, which is this orange one, and these both plots are the same, data. These are the same samples. They are basically jointly drawn at the same time. The only difference is that here I add them together, and here I look at the order statistics separately from another. If these 2 graphs, which here are plotted above each other, would be added up, I would exactly get this thing. And so, you see, this is some sort of line, right? And the mathematical answer to the question I posed in this way is here. If I actually sample it continuously, in this case I sample them continuously, but then I put them in this discrete bins, 20 discrete bins, in which way we get the dice back. But the solution to this continuous problem, if you look at it, you work around with uniform distribution. So the cumulative distribution is the identity function, blah blah blah, and you do your mathematics. You multiply the chance of both being smaller than the particular value to compute the distribution for the maximum. We are going to make this a little bit more formally later, but let it just be said that if I do this, I get out as a solution the beta distribution. And apart from this GIF, I also plot the beta here directly. And here in this case, for this simple case of having just 1 minimum, 1 maximum, and no other values. Jesus Christ! Not even my PNGs are loading. This is embarrassing. Come on. Okay, maybe I actually double click and then don't use the preview. That's a book. That's something else also. Come on. Okay. So the beta distribution for just using 2 dice rolls and looking at the first statistic and the second statistic, i.e. the maximum and minimum and the maximum, happen to be just actually some straight lines. So beta of 1, 2 is 1 minus x, and beta of 2, 1 is x. I'm not going to explain the beta label distribution, but I just describe the situation, and it comes out like this, right? So here is the chance of the maximum being the small value is in a uniform sampling from the continuous interval is small, and the chance actually grows linearly, and maybe with my explanation of looking of one dice after the other, it's sort of intuitive. But now, if you not just use 2 dice, right? Let's say you use then 4 dice, then basically if you again look at the maximum is pushed even more to the right? Because whatever 4 values you get from your dice rolls, you ignore the 3 lower ones, and they will land somewhere, and then the maximum has even a higher chance to be something large. So if you have 2 dice, let's say the mean was something around 14, now you get more rolls, and you have more you look at the most right one, and it has even a more higher likelihood to be on the right side of that, right? This is just a my vague intuition argument, but if you look at the formal math and look at the distribution, multiply them together, then that's fairly clear. If you do this process and compute the distribution, indeed you get these beta distributions. This is like sort of, at least in this discrete case, one of the ways in which you can define them. And for the 4 dice situation, or the vector with 4 elements, each being drawn from the uniform distribution, you get this picture, right? So now it's not just linear anymore. The products just come out like this. The minimum, this brownish one here. You look at the smallest value. Of course, it has the chance to be quite small, and so this goes up here. Whereas the second largest value, the orange one, it cannot, like, it's clear that the probability that this is a value going to 0 also goes to 0, because the sample from the minimum must always by definition lie below it, right? So you take these 4 values, you order them, you color them, and by definition the second one always has another value beneath it, and so it's intuitive that the probability that this goes to against 0 also goes to 0, right? For the orange one, for the second one to take on this value, 0.007 or whatever, there must lie another one, the first one, below it. So you get all these nice curves, and for this I also have the animation done here. You can sit through this because I think this is like sort of mesmerizing to look at. Again, should it not be clear, let me describe again what we see here. So I sample 1,000 values, but I sample them 4 at a time. I take the 4 random uniformly sampled values. I color them based on the order. The rightmost is always red, and the leftmost is always brown or beige. And then I just draw the distributions, so however the empirical distributions, however they show up here. In the right picture, and in this way I get back eventually, after a lot of samples and normalizing them, I would get back a curve which goes against the analytical beta distribution. Okay, and so now we have this sort of method to empirically compute the expected maximum, right? What would we do to compute the expected maximum? Well, we choose the distribution, in this case uniform distribution. The Python script, by the way, does not hinge really on it being the uniform distribution and the beta distribution coming out. You can choose any distribution on this unit interval. But you do this process, you sample 1,000 values, you box them in this case, 4, let's say. Then you have the maximum of a vector of 4 values. You get the empirical distribution out of it, this red line, and you can also compute it analytically if you know how, and we will discuss this. And then you have this distribution, and you normalize it, and then you can just compute the expectation value with respect to this red distribution. You just compute the integral over the value times the weight on all these points. So it's clear that the expectation value of this curve which goes up will lie somewhere around this area, right? And if I remember it correctly, in this case, it's actually at 0.83 or something like that. Okay, yeah, I have also sampled this for like higher numbers. So here I have done it for 10, although it gets really chaotic. Because on the right hand side, I plot these, oops. Okay, and I have even, come on. Jesus. I have even plotted these not next to each other, left and right, but on top of each other. Here you see better that I use the exact same samples. But in this case, it's 10 different lines, and so this is chaotic. And you see here on the bottom, they are overlaying, and so you don't see much except for the red one. I think I've also, for every one of those I've done the analytical computation, and it looks pretty. If you do an opacity filling, looks like this. And you see, I mean, you might know that beta distribution have this nice polynomial forms and normalization factor. Okay, so much for the animated GIFs. You have the script below. You can play around with that. Here, like in the last few minutes, a little bit of an analytical part. So again, I just want to remind you, you have some distribution. In this case, it's like a Gaussian distribution, but it can be anything. And if you integrate from 0 to some value a in this case, then you get some value below 1, and this is the cumulative distribution function. And so the value of the cumulative distribution function exactly gives you the probability of sampling a value that lies below a, right? So this is, to compute the maximum, you can already see that this plays the major role. You basically calculate stuff in terms of this cumulative distribution function. This is just a reminder. Here, if you're interested, below I have these numbers tabulated for the 20-sided dice. I have calculated this sort of by hand. So if you do this game with 2 dice, you get a mode, so a maximum likely roll for 20, and it's not even small, so it's like almost 10%. No, sorry, 10% is, that should be an equal sign. So here I drew smaller equals, but it should be exactly 20. Whereas for the median, which is basically looking at the chances that some value is exactly in the middle in terms of probability, what value gives you the probability to be on the left side of it is 50%, and that comes out to be between 14 and 15, and so by definition the 15 is the median here. And these two numbers, if you subtract them, also gives you the probability that you get exactly 15, which happens to be a little bit over 7% in this case. And the mean comes out like this. Okay, so let's talk about the actual theorem that I want to present in this video. So I actually, with the dice roll, it's basically uniform rolling and discrete for all the values. And I generalize this to take in not only like a more general distribution, not uniform, but also I allow that each of the, let's say you roll 4 dice, right? And you get 4 times sampling from a uniform distribution. I not only allow that we don't use the uniform distribution, we use a general distribution, PI. But I also allow that the different distribution used in these 4 cases are 4 completely different cumulative distribution functions, so 4 completely different distributions. And so this is my process. It's basically a random vector where each component follows a completely different distribution. I allow for that. Okay, and so if I multiply these distributions together, right, then I plug in some value a, then basically by the axioms of probability theory, then I get a function which gives the probability of a random sample like vector, 4 vector, having all components smaller than a, right? If I multiply the chances together that the one sample lies below a, then I get this the chance of all samples lying below a. So this is non-standard terminology, but I wanted to have a short name for this product, and so I called it pi. This pi of x gives you the probability that all values that you would sample lie below this input value x. And from this, basically out of the box, I mean, you formally you would have to argue a little bit, but it's completely clear, sort of by way of argument here, that then the expectation of the maximum function to this vector, right? So I consider xi to xn to be a vector of length n, where each component is sampled from your probability distribution. the maximum by a little bit arguing with the integral, the small slice distribution times dx. You can argue that the expectation of that has to be given by the expectation value with respect to the distribution that I just described. But I could now write down the integral and argue in terms of the values lying below it, but not above it, and so on and so forth. This is sort of the formal argument, but I hope it's fairly intuitive that this holds. And this is already basically the theorem I wanted to talk about. I think it's extremely pretty that you get that something which is somewhat complicated, right? That you have this maximum, which sort of feels like, it is a projection, but a more elaborate projection. You get one value out from the vector, but it's basically based on the value itself. It's sort of a complicated object. It almost feels discrete. I mean, it's not a discrete function in the component values, but it has sort of abrupt feeling to it, and nonetheless this gives something fairly similar. It's just another expectation value with a particular distribution, and so it is this kind of thing, the integral over the domain. I chosen minus infinity to infinity, but could probably be generalized a lot, the domain here. The x as in the definition of the expectation with respect to this distribution, to this measure, if you want. And then here I've written down a lot of ways to actually, rewrite this. So this pi is a product, right? So if you compute the derivative of that, you get a chain rule, so you get a sum of this thing times derivatives. And since the fat product is still there, you can sort of pull this out, and you have this kind of thing, and then you can play around with the derivative over the function itself. It's the logarithm, blah blah blah, and so you have a bunch of ways to express this. But I find all of this fairly nice, and also in the special case again that we actually looked at, where all the distributions are the same distribution. I chose even the uniform distribution for my GIFs, but just assuming that all these four values are from the same distribution, you get this super simple function where the complicated product, falls together to just this exponential of the distribution that you were originally working with already, right? So here you had the where you compute individual values that you sample, and then if you just take out one value, you can still work with your 1p and just do an integral over this somewhat complicated product, but nonetheless it's sort of simple. And I want to mention in conclusion, you can make this even more complicated, not just talk about the maximum, but talk about maximum, minimum, or even go into all the complicated order statistics where I also look at values. What is the probability that out of 7, how does the distribution for the fourth one look, and these kind of things. You get fairly more ugly formulas there, to be honest, a lot of sums and products. But it's also clear that here in this proof, we talked about the maximum, so we used the product of distributions, arguing that some value lies below the chosen value x with this probability. If you want to talk about a probability of something lying above x, compute of minimums and these kind of things, then you have factors of 1 minus p in this calculus naturally, right? So these products will not only, sums and products will not only be like products over these distributions, but also 1 minus the distribution. And this leads me back to the form of the beta distribution. So even if it did not, let me take one more complicated. Here, this is the situation with 3 dice, or with free uniform samples drawn from the continuous interval. Even if I did not do the formal derivation of the beta function itself, here you also have these sort of products of x and 1 minus x, and in the derivation the x is the value on the x-axis on the domain, but it is at the same time for the beta function is also probability, simply because drawing from the uniform distribution follows this completely trivial linear cumulative distribution function. Okay, I have talked enough, but I hope you find this cute and you can play around with this animation tool. So with that, I wish you a pleasant evening.